A quote from Albert Einstein: "Time does not exist. We invented it." The James Webb Telescope has now revealed what one of the greatest scientists of all time already knew 100 years ago. Time does not exist. Time is neither linear, real, nor determined in any way. Scientists are concerned because this means that the universe cannot be 13.8 billion years old. Could it be that space had no beginning and that the past does not even exist? Or do we live in an eternal present in which the universe has always existed? Based on current scientific discussions and several studies, a new cosmology is gaining ground. Led by physicist Professor David Wiltshire, a team at the University of Canterbury in New Zealand has announced that time is the real key problem in the current crisis in cosmology. The new timescape cosmology matches the current observations of the James Webb Space Telescope so perfectly in crucial areas that some experts already see the previously established lambda-CDM model being overturned. What exactly is timescape, and why is it more reliable than the old standard model? The lambda-CDM model describes the universe as a homogeneous, isotropic system with uniform expansion. In this model, the cosmos is driven by dark energy, which is thought to make up about 70% of the total energy content of a universe, but is still purely hypothetical. In recent years, in particular, there have been increasing observations that contradict this model, or at least cast doubt on its universal validity. Particularly prominent is the so-called Hubble tension, which shows that the expansion of the universe is not linear. Depending on whether the expansion rate is measured via cosmic background radiation or via supernovae in our local environment, contradictory values are obtained. The lambda-CDM model cannot convincingly explain this effect. If we also consider that dark energy and dark matter play a major role in old cosmology, and that neither has been proven, it quickly becomes clear that old astrophysics is lacking. Enter the timescape model. The new approach is based on Einstein's general theory of relativity, but takes into account the spatial inhomogeneity of the universe. In contrast to the standard model, which describes the universe as uniform, timescape considers the uneven distribution of matter. The theory explains that this irregular distribution of matter also influences the nature of time. This could shed new light on the many unexplained observations that have occurred since the launch of the James Webb Telescope. It could also explain other phenomena that have long puzzled scientists. In the new theory, the way time passes is influenced by large structures. Light and matter appear to occur in temporal sequences, but this could be a mistake. The research group led by David Wiltshire now argues that time passes faster in low-density regions, such as cosmic voids, than in denser areas, such as galaxy clusters. This creates an effect that makes our observations appear as if the universe is expanding at an accelerated rate. If this is true, the idea of dark energy would be invalid. This distorted perception of time could also be the key to explaining the Hubble tension and other anomalies, such as bulk flow, the large-scale, unexpectedly rapid movement of galaxies, without resorting to additional and unproven forces. Timescape is reality, and voids are the proof. It sounds like pure magic. Matter and structures influence the passage of time. This fits in with the assumption that time is a highly questionable scientific concept anyway. The stubborn nature of time can be observed in fantastic phenomena in the universe, but also, quite mundanely, in our own perceptions. Albert Einstein liked to use this example to illustrate the nature of time. If someone is sitting on a hot stovepipe and cannot get down, every second is agonizingly long. If, on the other hand, someone is enjoying themselves with a lover, time passes much more cheerfully and quickly. Now these observations of the relative appearance and effect of time could be followed by another leap forward. A 2017 study by Wiltshire and his team tested timescape against real observational data, such as supernova distributions and cosmic structure formation. The result: in several cases, timescape provided a better match with the data than the lambda-CDM model. More recent studies looking at the so-called KBC supervoid also suggest that our Milky Way may itself be located in a giant void. This, too, could explain many of the apparent contradictions in the observed expansion. What makes the timescape model special is not only its mathematical certainty, but above all, its greater proximity to observable reality. At a time when the standard model is coming under increasing pressure, the scientific relevance of the model has been proven many times over. Timescape is not just some new concept, nor esoteric or science fiction, but a testable and seriously developed new physical framework, one that works precisely where our current science fails. And because timescape is also based on the old guidelines of relativity theories and essentially revolves around the very force Einstein once doubted, it could soon replace the lambda CDM model, or at least form the basis for new ideas. Another advantage is that timescape can explain cosmic voids, huge, almost empty regions in the universe, and other superstructures. Voids are so empty and so large that they pose an extreme challenge to our current scientific understanding of structure formation and space-time dynamics. Voids often extend over hundreds of thousands to several million light-years and contain only scattered galaxies, while enormous filaments of matter surrounding them cause mass accumulations of galaxies. Such extreme distributions of matter contradict the old lambda CDM model in a problematic way. The lambda CDM model assumes that the universe developed relatively homogeneously after the Big Bang, with small, evenly distributed density fluctuations that evolved into today's structures over billions of years through gravity. Voids do not really fit into this model, at least not in the form observed. Most of the superstructures observed by the Webb telescope in the young universe also do not fit into this model. Voids are too symmetrical or too frequent to be mere statistical coincidences. Furthermore, highly peculiar effects occur in voids, such as light being distorted and redshifted differently on its journey through the void than in the rest of the universe. Even stranger, galaxies in or near voids appear to move so fast that the standard model fails again. The large, mysterious voids have already been described as active disturbances in our cosmological model, and timescape could be the solution. Let's look at the phenomenon of time around voids. Instead of expanding uniformly everywhere, voids are demonstrably expanding faster than denser regions. To an observer located within a void, for example, us, the universe would appear to be expanding at an accelerated rate overall. But this impression would be an illusion caused by time distortion. The hypothetical dark energy would then be an artifact of scientific explanatory failure and observational error. If we are indeed located in the KBC supervoid with the Milky Way, we would be in exactly such an observer position that leads to this optical distortion. The different time structure would then depend on matter distributions, structures, and the position of the observer within a dense or thin region of the universe. This raises profound questions. Can we even derive an age for the universe under these circumstances? Does the universe even have an age in this sense? Does the question of age really matter for our research? Time is definitely a problem in science. Another quote from Albert Einstein: "Time and space are not the conditions in which we live, but the modes through which we think." Time is one of the most everyday and, at the same time, most mysterious concepts in physics. We experience time as seemingly linear, as a chain of moments flowing from the now into the future. We also perceive what once was as the past. But as soon as we try to define time objectively, we run into problems. Physically speaking, there are several concepts of time that differ slightly depending on context, and sometimes even contradict each other. In Newton's classical physics, time was an absolute measure. He assumed that the nature of time must be the same everywhere in the universe, meaning that time always passes at the same speed and independently of movement or location. This idea was refuted by Albert Einstein, who proved with his theory of relativity that time is not absolute, but relative. It passes differently on a material and universal level, depending on gravity and speed. The stronger the gravity or the faster an object moves, the slower time passes relative to an outside observer. This effect is negligible on Earth and in the nearby cosmos, but the differences have nevertheless been experimentally proven using clocks on airplanes and satellites. Einstein himself went on to say, "The distinction between past, present, and future is only an illusion. albeit a persistent one. This statement also touches on the philosophical problem. Time may not be a fundamental component of reality, but rather an illusion, a construct of our consciousness that arises when we observe space-time structures from the wrong perspective. Modern consciousness research even goes so far as to assume that we humans project reality, and thus time and space, from our consciousness. This would prove Einstein right when he said that time and space are modes of thought, not realities. In quantum physics, there is no clear definition of time. Many equations work timelessly, as if time did not play a role. Quanta do not know time, and can exist in multiple times and places simultaneously, as if the dimensions of time and place do not exist, or at least not as absolute or reliable quantities. In thermodynamics, time appears as entropy, as the arrow of time. Time shows a dynamic that moves from order to disorder. But even this arrow of time is not a fundamental quantity or direction. It merely describes a probability. When we use time as a yardstick to describe the universe, as we do when calculating its age or the expansion of space, we assume that time passes uniformly and synchronously everywhere. However, observations such as time dilation and models, such as timescape cosmology, show that this assumption must be flawed. Time can vary from region to region. This raises the question of whether there is even such a thing as objective time for the universe, or whether each region has its own cosmic now.